Okay, let's start for today's class. See, last day we have completed the strobe and handshaking method, and the rest of the part will complete today and we'll learn some new things. Okay, first of all, we'll learn about IO interface. See, whenever we are discussing about data transferring or executing any kind of instructions and all, there always should be an interface which will help us to transfer data or which will help us to do any or execute any instruction. See, IO, that is input output module, and the processor, these two are two different modules. There should be some interface like this. I am the teacher and you guys are the students. So there should be an interface which is Google Meet, by which we can contact each other. Otherwise, how can we discuss the class and how can we discuss the syllabus? There should be an interface for everything, every two module which are to be contacted with each other. So that is the main point over here. Even about the IO interface is because of that. See, the method is that is used to transfer information between internal storage and external input output devices is known as input output interface. Simply, this is a logic, this is a way of communicating between input output devices and about the and for the processor. Now, the CPU is interfaced using special communication links by the peripherals connected to any computer system. See, whenever we are instructing CPU to do something, it needs some input output device to, take the inputs from the user and to show the outputs to the user. So it has to interface with those modules. And by communication links, special communication links, CPU does this interfacing. Okay. Now, these communication links are used to resolve the differences between CPU and peripheral. Peripheral means itself the input output devices. Okay. Anything, any module other than the central processing unit is known as peripheral, like input output printer, monitor, mouse, whatever it may be, doesn't matter. It is the input output devices which we call the peripherals. Now, there exist special hardware components between CPU and peripherals to supervise and synchronize all their input and output transfers that are called interfacing units. See, whenever we are interfacing, we need some special kind of hardware. Like we need some buses, bus as in not the bus we ride for to go anywhere. Yes, these are the buses which instruction writes those buses to transfer them from one module to another module. These buses do the interfaces. So input output interface is very important. In this interface, we have three modes of transfer. Whenever data is transferring, there should be a proper mode of transfer from CPU to input output. Okay. First of all is programmed IO. Second of all is interrupt initiated IO. And third is direct memory access, which is DMA. First one, programmed IO. See, in this case, what it is done is whenever CPU is needed an IO device to operate for an instruction, there is small programs or subroutines written in a special memory place for that particular input. Suppose we have given the instruction to CPU to display something in the monitor. So CPU needs the monitor to display something. The special routine or program will be written in a special memory area to call the processor to access the monitor, so that CPU can access the monitor easily and display whatever we need it to be displayed. Okay. So programmed IO, please read it carefully. I have prepared the slide in that way only so that you can read it and grab the basic concept. Okay, and then you need to study the books. If you don't study the books, you won't get the concepts clearly. My slides are only to discuss you briefly, introduce with the topic, and I'll explain it to you. But you have to study hard from the textbook, because textbook will explain you properly. These slides cannot explain you properly. This will give you brief idea. And if you need to pass your exams or you need to learn something, you obviously have to follow any textbook. Let it be TK Ghosh, let it be Mano, doesn't matter. You have to follow a textbook. So for programmed IO, yeah, if anything you want to tell me, anyone? Someone's mic is on.
Victor Mogere দেখলাম 55টা না 50টা রিভিউ এসেছে।
Rick, I think your mic is on and it's keeping some knowledge.
যদি ওই ভার্চুয়াল মিটিংটা
Please turn off your mic, Rick Sarkar. He's not even there. I don't know how you guys are going to pass your exams, whatever. Programmed IO. It is due to the result of the input output instructions that are written in the computer program. Each data item, please read it carefully, you will understand. Each data item transfer is initiated by an instruction in the program. Usually, the transfer is from a CPU register and memory. In this case, it requires constant monitoring by CPU of the peripheral devices. In this case, the input output device does not have direct access to the memory unit. Obviously, it has a special program to access the memory, not directly access to the memory itself. A transfer from input output device to memory requires the execution of several instructions by CPU, including an input instruction to transfer the data from device to CPU and store instruction to transfer the data from CPU to memory. See, in programmed IO, what CPU does, it keeps monitoring. It keeps monitoring whichever instruction is being executed. Whenever one instruction is being executed, it directly gives the access to input output to the memory so that it can access the memory and execute the instruction properly. But what is the problem over here? The CPU has to keep monitoring properly. Time to time it is busy with monitoring the program, which instruction is being executed. So it will take some extra time or extra load of the CPU, right? Now, the CPU stays in the program loop until the input output unit indicates that it is ready for data transfer. This is a time consuming process. Obviously, when the CPU is busy with monitoring something, this will take time, because the CPU is taking time to monitoring an instruction to be executed. It is keeping monitored the instructions where it is written in the program and where it should be stored afterwards. It has to keep monitoring everything. That is why this is a very time consuming process, and it keeps the CPU busy needlessly. There's no need of keeping everything monitored. If we have some other process to execute this same thing, the CPU does not need to be busy every time. It will just give extra load to the CPU. This situation can be avoided by using the interrupt facility. See, in the name it is written, interrupt initiated input output. Whenever an input output device needs to access the memory, what it does, it will interrupt the CPU. See, I have to, if you suppose when I'm giving this lecture, you are listening. Whenever you are arising a doubt, You just directly asking me, ma'am, please explain this once more. Ma'am, I couldn't understand this. See, you are interrupting. If I am asking you, multiple times, are you understanding? Are you getting it? Then it will keep me busy with that only. I cannot teach you while I'm asking you questions. So isn't it obvious, if you interrupt me, instead I ask you every time, are you getting it? Are you understanding it? It will be easier for me and both of you. Like, if you interrupt me in the session of lecture, that ma'am, I couldn't understand this. Same thing has happened with interrupt initiated input output. See, whenever interrupt is happening with CPU, input out, that means one input or more than one input output device is needed the CPU to access the memory. So that is why interrupt initiated IO is somewhere better than programmed IO. In programmed IO, what we were doing was keeping monitored by the CPU whenever the input output is needed to access the memory, and CPU was busy doing this, and that was an extra load to CPU, which will may cause the slowdown of every process. Whenever CPU is busy with some process, it will definitely slow down with other process. So that is why interrupt initiated IO is better than programmed IO technique. Okay, now that is what is written. I'm not going to read each and every line, just read it once. What I have explained it to you, that is only written here. Now, some other special notes about this. Both methods, programmed IO and interrupt driven IO, what is interrupt initiated IO, require the active intervention of the processor. See, we are saying that processor has to be interrupted. Processor has needs to keep monitoring. There is no directly access to the memory from the input output device. So that is where the problem arises. Whenever an input output devices need to access the memory, it need to disturb the CPU. See, I have to access the memory, please give me permission. Right? If, suppose, if I am keeping these slides to myself, then whenever you will be needing to see the slides or see the notes, you'll have to ask me, please ma'am, share that part, please share your screen, ma'am. That is a bit, hazardous way of handling any intervention interfacing. But if I give this slide to you guys, then you can access it whenever you want. If I upload it to the Telegram group, then you can access it whenever you want it to be accessed. Then the concept of direct memory access came. This is how it came. To, slow to not slow, to reduce the load of CPU. Like, every time any input output device is interrupting CPU, any input output device has to be monitored by the CPU. CPU has to do so many things. CPU has to execute instructions, CPU has to fetch the instruction, decode it. Already so many things are happening in CPU. If we could reduce the load somehow, that will increase the speed of the processor itself. That's why the DMA came into picture. What it does, the data transfer between a fast storage media such as magnetic disk and memory unit is limited by the speed of CPU. Obviously, if the speed of CPU is less, if CPU is working so many things working with, then how can it provide a high speed access to the memory for input output? That is why, if we give direct memory access to the input output device, then it will be a speediest job to be done. Thus, we can allow the peripherals directly to communicate with each other using the memory buses. And now, what is the memory buses? What are these? These are some buses which carries the instructions to be executed. Any bus in the CPU is just like the bus we use to ride in local road. Any bus, what does buses do? Just take us from one place to another. Similarly, these memory buses or address buses takes the instructions or data from one place to another. Let it be IO, let it be CPU to IO, let it be IO to CPU, whatever it may be. Doesn't matter. Buses are used to transfer the instructions or data from one place to another. Okay? Now, if direct intervention of the CPU is omitted by giving the direct access of memory to the input output device, obviously the speed will increase. This is how direct memory access or DMA came into picture. This part we have left in the last lecture. Now I'll continue with another one. Is this visible? DMA block diagram?
Yes, ma'am.
Okay, thank you. Okay, see, people are keep coming. It's 10:51. Please tell your friends to come on time for my class. I'm very punctual person and I like to be punctual. I spare 5 to 10 minutes every day. But many of you guys are late, still late. So I won't allow. It is very disturbing when I am giving a lecture and you are keep coming. Okay. Now, next. This is DMA block diagram. See, there are various components in DMA block diagram. I'll explain each and everything. As of now, you just see the diagram. I'll just explain it you afterwards. First of all, there should be two signals. These are bus request and bus grant. As I told earlier, bus request. Buses are the medium by which we can transfer the data from one unit to another unit. Let it be peripheral to CPU, CPU to peripheral, or peripheral to peripheral. Okay. Many times we need to access two peripherals at the simultaneous time. Suppose we are instructing the printer to print. We are accessing the mouse and monitor at the same time while the printing is happening. So we need to access the peripherals simultaneously, more than one peripheral simultaneously. That's why the buses are very important part in DMA. Bus request and bus grant. What bus request does is, whenever direct memory access, whenever any peripheral needs to access the memory buses to transfer any data, it requests for the buses to give the access. And bus grant, in the name it is written only, it will grant the access. If it is enabled, that means the grant has been it has been granted to be accessed. The buses granted to be accessed by the peripheral. Okay. Next is address bus. Obviously, address, whenever I'm living anywhere, there should be a special address space there. Suppose I'm living in an apartment. The apartment contains 28 flats. Okay. If the 28 flats has a specific address, suppose the apartment name is, UEM. Suppose UEM apartment contains 28 flats. If every flat is named like UEMA, UEMB, UEMC, UEMA1, UEMB1, like this, every flat has a specific address from a range, in a range, because this this contains only UEM. There are several apartments in the city, but in UEM there should be an address space to be accessed. So the address buses are for that purpose. Which address I have to access in the memory? There should be a specified address for every instruction. I have told it in the earlier lectures that there is a specific address for every instruction which is to be executed next. So whenever the specific address we know, we have to access this. We means the peripherals has to access it by the buses. And the data bus. See, the instruction has a specific address, and the data where the data is stored, that should be a specific address, and the data bus should be there to carry the data. Address bus will carry the address. Address is also a data, but address bus will carry the address only, and the data bus will carry the data containing the address or the data wanted by the instructions. That is why there are two types of buses. One is address bus, one is data bus. Now, One signal is for read and one signal is for write. Read, write, why it is needed? Or every time we are executed an instructions, every time we are doing it, either we are reading it or we are writing it or we are doing it both. If we are adding it, then we are writing the data. Obviously, if we add something and we are displaying it to our monitor, then it must be some data which has been written recently. And how can it be written if it is not read previously? So the main agenda over here is we have to read or write or do both for every instruction. So we need these two signals for that purpose. Now, let's move on to the next slide. This is the mechanism. I'm going to explain it to you slowly. As I have told earlier, the bus request signal, it is used by the DMA controller. Which controls the DMA is the DMA controller. DMA is a mechanism which is controlled by DMA controller to request the CPU to relinquish the control of the buses. CPU, what, who has the control of the buses? Obviously CPU. CPU is the mastermind of everything is our in our computer system. So whenever the input, output or peripheral, whenever any peripheral needs to request the bus, it will request to the CPU, please grant me the buses. If the buses are free, then the bus grant request will be enabled. If the buses are not free, it will keep on holding, and whenever the bus is free, then the bus grant will be enabled by the CPU. Now, whenever the bus grant is enabled, there is no intervention of CPU is needed anymore. Directly access to the memory will be given to the input output device or any peripheral. See, there are several modes of transfer in DMA. Previously, what we have studied, mode of transfer in the CPU. Three types were there. Number one was programmed IO. Number two was interrupt driven IO or interrupt initiated IO. And number three was direct memory access, which is direct memory access is called also DMA. And now we are talking about mode of transfer using DMA controller, which is first one is bus transfer, second one is cycle stealing, and the third one will be interleaved mode. I am going to describe each and every one in a short way, then you'll read it and you'll understand it. First, bus transfer. First of all, if a chunk of data is to be transferred, please listen to me carefully. If a chunk of data is to be transferred by the peripheral, then what DMA controller does it keeps a register of byte count. That means how many bytes has to be transferred in this short time interval. Yeah, if anyone wanted to tell me anything, I guess no questions. Fine. The bus transfer, whenever, see in the name, burst means a chunk of data. A chunk of data is transferred whenever it keeps a register to count the data bytes. One byte is transferred, second byte is transferred, 3 bytes are transferred. Whenever every byte has been transferred, the bus grant will be released. The buses will be released. Other than that, the buses will be occupied until and unless the transfer is being completed. Again, I am repeating. Bus transfer mode has a chunk of data and a register which is keeping the count of bytes for the DMA controller to transfer the data. The register counts the bytes 1, 2, 3, 4. Whenever the count is came to 0, I mean the count is in negative way. Suppose I have 100 bytes to be transferred, then 100, 1 byte is transferred, then it will be decreased to 99. Then 1 byte is transferred, then it will decrease to 98, then 97, 96, 95. When it came to 0, then the buses which were granted by the CPU to the peripheral will be released. Will be released as the work has been completed. This is burst transfer mode. So if we consider the total time taken to transfer the total memory is first the bus grant request time. If we request the CPU, please grant me the buses. There can be two ways. If the CPU is, granting at that moment instantly. If it is not, then it will wait to grant for the CPU. So it will take some time. In to plus n bytes to be transferred. N into memory transfer rate. There should be a memory transfer rate in which speed, how many bytes per second or per unit time is being transferred. N bytes are there. So the total time will be taken will be n into memory transfer rate plus bus release control time. After transferring the memory, we need to release the control of the buses. So this is the total time taken by bus transfer mode. Next mode for the DMA is cycle stealing. See, the concept behind cycle stealing is hidden in the name only. I have always told you to follow your instinct, to follow the names, keep the meaning. Cycle means, I have told in the previous class, every instruction here in the CPU is executed by cycle times. 1 clock cycle, 2 clock cycle, 3 clock cycles, like that only. Clock cycles are the unit times to execute any instruction. One instruction may take one or more clock cycles. So, whenever one instruction is being executed by the CPU, what DMA does is it steals the cycles from the CPU. Suppose the CPU is executing one instruction and in that execution it needs 10 clock cycles. What DMA does, whenever the CPU is executing, it steals one cycle after some time interval. For one cycle, it will transfer some data. Again, suppose we are talking about 100 clock cycles to be executed by the CPU. Okay, let us say the DMA will work in cycle stealing mode like this. For every 10 cycles, it will steal one cycle from the CPU and transfer some data. So there is no specific, rate of transfer. In one clock cycle, how much data it can transfer, the DMA controller, it will send it. And after one clock cycle, it will stop. Then again, it will wait to steal a cycle. So it is stealing of the clock cycles. That is why it is called cycle stealing. So how much time it may require? First of all, it will always, request the bus. Whenever the CPU has requested, granted the bus grant signal, then one bus cycle to transfer the data. It doesn't count any data, register or how many bytes are being transferred in single clock cycle, doesn't matter. In one clock cycle, it will transfer data. And until and unless it is just the data, all the data has been transferred, it will keep doing this cycle stealing thing. And the time to require to release the bus. See, these two are common in both of the modes. Cycle, in cycle stealing mode and bus transfer mode. First one is to time required to bus grant, and the last one, time required to release the bus. The idea is different in the middle part. Here, one bus cycle will send the data, and in the bus transfer mode, what was we doing? The DMA controllers was sending the data, whole data at a time. How much time it requires doesn't matter. It will send the whole of the data at, together. And in cycle stealing mode, it will be done time to time. After every 10 to 12 cycle, it will steal a cycle from CPU. Cycle is nothing but a time limit. Okay. Now comes into picture another mode, that is interleaved mode. What interleaved mode does is, suppose we are adding. I am just giving you example so that you can understand. Suppose we are adding. We have, fetched the instruction and we are not using the CPU buses anymore. Then the DMA what does it? The DMA, when saw that the CPU is not using the buses anymore, it transfers the data until and unless the CPU is again demanding the buses. Suppose when we are adding two data, when we have fetched the operator and operands and decoded it, we don't need the buses anymore as of now, because we are doing the calculations in the ALU, arithmetic logic unit. We are doing the addition calculations in the ALU. That is why we don't need the buses right now. So the DMA keeps monitoring about that. Okay, now the CPU is not using the buses. Now I'll send the data. Then this is called interleaved mode. In one instruction execution, some part will be used the bus of the memory, some part will be used by the CPU, some part will be used by the DMA controller. That's why it is called interleaved memory fashion. This is called interleaved mode. That, you know, first is CPU, then it's DMA. Again, the CPU is using buses. Next, it's again DMA. Again, the CPU is using buses. Again, DMA. It's interleaved with one another. It doesn't need another cycle or another bus time to transfer the data. The DMA is very smart to handle it. It's a very complex, technique to be executed. Still, this is the most efficient way because it doesn't need to any extra time to transfer the data. The DMA is doing it in between execution of an instruction. That's how the time is saved. The bus utilization is the most at top. That's why it is the most efficient manner to transfer the data. Okay, these were the three modes of transfer of DMA. Okay, so what have we learned until now? First of all, mode of transfer of CPU, that was programmed IO, interrupt initiated IO, and DMA. For DMA, we have seen three modes of transfer. Number one is burst mode. Number two is cycle stealing, stealing the cycles from CPU. Number three is interleaved mode, the most efficient, most complex because it is interleaved within one instruction or several instructions. No extra time is required in interleaved mode. That's why this is the most efficient way to DMA controller to transfer the data. Next, one technique we need to study about is polled IO. What is polled IO? Whenever one peripheral is to be accessed by the CPU. CPU as peripheral needs the memory buses and all. CPU also needs the memory buses and peripherals to be accessed. So whenever one peripheral has to be accessed with CPU, then what CPU does it polls, are you free? Are you free to be accessed? If one of your student, I'm just giving an example, then it will make sense. If I need to access one of my students right now, I'll ask, are you free? Are you free? I'll ask. If he or she is free, he'll answer me, yeah, I'm free to do some work. You asked me. Then I'll give him or her some work. Like that only, CPU will ask the peripheral, are you free? With a signal. It cannot talk, obviously, so it will ask with a signal, input output request. Busy or ready. These are two signals for CPU to ask the input output that it is free or not by polling. This is polled input output. This is a technique to know the CPU that if the input output is free or not. Okay. Next technique, some communications ways of CPU. This is very important. As CPU needs to communicate with various memory and input output devices, as we know, data between the processor and these devices flow with the help of the system bus. Obviously, they are the mediums. There are three ways in which the system bus can be allotted to them. What are the three ways? Number one, separate set of address, control, and data bus to input, output, and memory. See, whenever input, output, and memory are accessing the data bus and the control buses and the address buses, there are two ways. There are basically two ways. One is having a common set of bus for both and memory and input output, and one having separate buses for memory and input output. Why this is happening? Whenever we have common buses, we need to wait. When memory is using the buses, we can IO cannot use the buses right now. When IO is using the bus set, then memory cannot use. But then again, this will reduce the cost, reduce the address space, reduce the size of the CPU. So that is why separate common bus is technique is used also, and separate bus technique is also used depending on the architecture what we need to do. If there are separate set of buses, there is no need to any intervention of CPU, sorry, in any intervention of CPU, yeah, right, any intervention of CPU between memory and IO, that which buses is to be used right now, who will use the buses. See, I am your teacher. If I am teaching you right now and some other people, then it will be confusing. If you are accessing me, then they can't access. If they are accessing me, you cannot access me. So, but I am one teacher and I have one time to spare, then I have to do in this way. I have to keep you busy once at a time, then I'll answer to them once at a time, like this only. But if I have time to spare two classes, then I'll give you separate class and I'll give them to separate class. This is how this works. Providing different buses, it will provide. If it doesn't have that space, that it won't provide, it will use the common buses. From this way, we have two concepts: one memory mapped IO, and what is isolated IO, or it is also called IO mapped IO. Memory mapped IO, the buses are common. The address space shared by the CPU and the input output device are common. Okay. So here is the picture. The diagram is, see, this is the address space, memory and IO. Memory is the one who is having three buses basically: control bus, data bus, address bus. Address bus will contain the addresses, data bus will contain the data, and control bus will contain the control of the CPU. How much time it will require to CPU to be execute instruction to be executed, these controls will be provided by control bus. And IO needs to take permission to the memory if one of these buses are free, so that it can use these buses. And for isolated IO, see, there will be no control bus. Why this control bus is needed? Control bus is needed to give the control of the address and data bus either to memory or to IO. I am repeating myself. Here are three types of buses in memory mapped IO. One is address bus, second one is data bus. What it does, I have already told you. And one is control bus. Control bus will give the access, will have the power to give the access, the data and address bus either to memory or to IO as per the requirement, as per the scenario. Okay. Next, for isolated IO, what it does is there are two sets of bus, address bus and data bus, and both have different sets of address bus and directly connected to the address and data bus. These are single lines, but sets are different. Okay. So whenever IO needs to access it, it doesn't want to, doesn't need to take any permission or any kind of, waiting time to access the address bus or data bus. And similarly, for memory, it's also the same. It doesn't need to wait for IO to complete the task and then it has to access. It can access directly. This is more efficient, but it is, again, it is taking extra hardware logic. But this is not taking extra hardware logic, memory mapped IO, as this is, space is reduced. Here, extra space is needed. So these are the basic thing of isolated IO and memory mapped IO. Here is a small comparison between them, very important for the exams. And what I have told you, that is only written here. Please have a read. If you have any problems, you can tell me directly. So, as of now, this particular chapter of module 4 is completed. What have we learned in module 4? First one was the, hardware and microprogram control. Then we have learned about the strobe handshaking mechanism. Then we have learned about the modes of transfer by CPU, programmed IO, interrupt initiated IO, direct memory access. Then we have learned about direct memory access mode of transfers, burst mode, cycle stealing mode, interleaved mode, and lastly, we have learned about pooled IO mechanism and memory mapped IO and isolated IO or IO mapped IO. So this is the module 4 completed. Now I'll be giving you the quiz link. Wait for a while.